Hello, everybody, and welcome to the second of the Earth Systems and Climate Change Hub's Climate Matters webinars. My name is Sophie Schmidt, and I work as the Communications Officer in the Hub, and I'll be your host for today. Assisting me behind the scenes, though, is Sonia Bloom, Knowledge Broker within the ESCC Hub. Hi, Sonia. If you do have any technical questions or issues throughout the webinar, please shoot Sonia a message in the chat function of WebEx. And before we do get started, just a few small housekeeping issues. If you could please ensure you are on mute throughout the presentation. You are very welcome to leave your video on if you would like. The webinar will start with around 30 minutes of presentation from our three speakers, and we have 30 minutes allocated for questions and discussion at the end. So at any time throughout the webinar, you can post questions and discussion points in the chat box. The questions there will be used for this session at the end of the presentations. Or you can raise your virtual hand to ask a verbal question during the Q&A session using the WebEx hand raising tool. Please note that this webinar is being recorded. A copy of the recording will be made available on request and we'll likely post it up on our YouTube channel over the next couple of weeks. But before we do begin, I'd like to acknowledge the traditional custodians of the lands and seas on which all of us here today live and work. And I'd like to pay respect to their elders, past, present, and emerging. I extend that respect to Aboriginal and Torres Strait Islander peoples here today with us. And I'd like to acknowledge the strength and resilience of First Nations peoples in adapting to the changes and threats to country from climate change and from climate variability. So this is the second webinar in the new Earth Systems and Climate Change Hub Climate Matters webinar series. If you haven't joined us before, the webinar series provides an opportunity for researchers to showcase their achievements throughout the lifetime of the Hub to our Hub staff, researchers and key stakeholders. It's aimed at sharing our science findings and discussing linkages and future opportunities. So today's webinar will discuss climate variability and change. Our presenters are Argus Santoso from UNSW, Ailey Gallant from Monash University, and Pandora Hope from the Bureau of Meteorology, all of whom contributed to the Hub Project 5.2, which was Understanding Climate Variability and Change for past, present and future. So Argus will be starting the webinar and over to you, Argus. Thank you.
Thank you very much, Sophie. Yes, hi everyone, good afternoon. I'll be opening this presentation on behalf of Christine Chung. So we're talking about NESS Project 5.2, Understanding Climate Variability and Change, Past, Present and Future. So next slide, please. Yeah, so I'll be introducing this project overall. So what is the challenge? We're looking at the challenge that we need to tackle as a project. Basically, Australia is uniquely located, it's geographically unique. It is surrounded by oceans, Indian Ocean, Pacific Ocean, and Southern Oceans. And in the north, there's the Indo-Pacific whirlpool, which drives the global atmospheric circulation. And so Australia is surrounded by so many climate drivers. There's a El Niño Southern Oscillation in the Pacific, Indian Ocean Dipole, Southern Annular Mode. And we're trying to understand in this project the dynamics and impacts of these climate drivers. And we want to develop also attribution science to better distinguish between natural variability and climate change, the signals that drive extreme events. Thirdly, we would like to provide tailored data, information and associated technical advice on the impacts of climate variability and change in Australia. So the key highlights that we are going to talk about today, I will first speak on understanding the El Niño Southern Oscillation and Indian Ocean Dipole and how they contribute to extreme events, how they may change in the future. And Ailey will talk about identifying risks and factors leading to drought in Australia, from flash droughts to multi-year droughts. And to conclude, Pandora will talk about attribution of climate extremes and new techniques to attribute to climate change. And she will close the presentation as well. So next slide. So the key challenges for ENSO and IoT project, basically motivation is that if you look at the right-hand panel, the picture, if you that's basically the climate patterns associated with ENSO and IoT. Okay, so during El Nino, during El Nino, Australia tends to be dry, as indicated by the brown contours, right? So, and Indian Ocean dipole, positive phase of Indian Ocean dipole, Southeast Australia tend to be dry, and you can see how those climate phenomena correspond in terms of sea surface temperature. Okay, so because of this impact, we are very concerned because Australia is prone to climate extremes. And in the backdrop of that, the greenhouse gas emissions keep increasing. And greenhouse forcing can actually alter the way this climate variability works. And it can lead to extreme events, increases in extreme events such as droughts and bushfires, also floods, of course. And so it's this critical for us to investigate how ENSO and IoT operate, how ENSO and IoT are simulated in current generation of climate models that are used to make the future projections, and how the mechanisms and impacts are changing in a warming climate. Okay, so next slide, please. How are we going to tackle this challenge? So the first, the approach that we implement is on a large, the key approach basically is to analyze observations and climate models. And the purpose is to first understand observed events and their implications. For example, we do not know sufficiently how ENSO and IoT work because we do not have enough events in the observations. For example, in the 2015-2016, there was an El Nino event, and it turned out to be an extreme El Nino, which is depicted in that time series of sea surface temperature average over Eastern Equatorial Pacific. And you can see 1982 and 1997, they were the, before 2015, they were the, the biggest extreme El Nino. And now came 2015. But it turns out, we did research on that. It turns out that the extreme 2015 El Nino is actually a mixture between Eastern Equatorial Pacific El Nino and a Central Pacific El Nino. And so we had a workshop bringing together researchers across the hub. So that picture there were 25 researchers from Bureau of Meteorology, SARO, UNSW, NESS, UTAS, and trying to identify what knowledge is lacking in understanding ENSO. And one very important aspect is event diversity, how ENSO events are different from one another. And that has very important implications for prediction. And similarly, for the IoT, it turns out that it also has an event diversity as well. And that is a new research frontier. And the 2019 positive phase Indian Ocean dipole, in that, no, going back, not yet. In that time series in Wang et al. 2019, sorry, Sonia, in the previous slide. Yes, I'm still here in this slide. Okay, the 2019 extreme positive IoT, we had a research paper trying to understand what drives it, what makes it extreme. And it was distinctly different from the previous extreme IoT, such that occurred in 1997. It turns out to be a very strong latent heat flux that make it an extreme one. And also 2019 extreme positive IoT was preceded by a positive IoT, 2018. At the same time, 2018 and 2019 were a Central Pacific El Ninos. And this combination actually was the important factor that gave rise or fueled the Black Summer bushfires in 2019. Okay, next slide, thank you. And I just highlighting that top panel is a research review. We had a workshop, 3 workshops, bringing experts together, trying to understand the implications of ENSO diversity on South American climate. Okay, second approach is to look at multimodal assessment, SIMIP 5 and SIMIP 6, to identify which models are able to simulate ENSO and IOD event diversity. Not every model can do that. So we have to identify these models and then use these models to make future projections. And one last point I want to mention is that our project is the first to use the Access CM2 model developed by NESS 5.1 for climate experiments. That was used by Christine Chung, published in Scientific Report. She basically took this model and clamped the temperature and salinity in the South Pacific towards climatology. What that means is you basically kill the variability. And what is the result? The decadal variability is weakened, and also there's a reduction in the extreme El Nino and extreme La Nina. It demonstrates that what's happening in the equatorial Pacific is also impacted by other regions. This is another paper that I want to show here, a paper in Science led by Chai. We also had workshops. So we have lots of workshops, basically putting everyone together and try to identify the scientific challenges. And without, I don't want to spend much time on this, so I think we better move on to the next slide. Okay, the key highlights that I want to talk about today is about future projections of ENSO and IOD. So previously, research have shown that there was actually a lack of intermodal consensus. Models do not agree on what's going to happen with ENSO in the future. Some project weakening, some project strengthening. But besides that, we found that there was actually an increase in the frequency of extreme El Nino and extreme La Nina events. But that's old story. So what is new? We recently found that actually, if we look at sea surface temperature variability, which is the aspect that models do not tend to have any agreement among each other, there was actually an increased variability in Eastern Pacific ENSO. And how do we find, how do we go to that conclusion? Is that we need to distinguish between Central Pacific and Eastern Pacific events. So once we do that, and we identify those models that can simulate those events, we found an increase, as you see in this right-hand panel. Almost all models that were selected show an increase. So blue was past, red for future, right? And those increases stem from the increased occurrences of strong El Nino events in the bottom panel. Okay, another new research that I want to highlight is this idea that the role of internal variability is like the butterfly effect. So if we start off from initial condition, but you just perturb those initial conditions very little, over the next 50 years, the ENSO projection will be different. The ENSO variability is different. So we found that if you start off with a weak ENSO variability, in the future, you will get projected strong El Nino ENSO variability. But if you start off with a strong ENSO variability in the beginning, then in the future, you will get a weaker projected ENSO variability. And that is driven by the nonlinear effect of ENSO itself. So ENSO is able to modulate its own behavior. That makes it challenging for future projections. And the third point is about coming back to extreme El Nino events based on convection over the Eastern Global Pacific. And it's that if we limit greenhouse gas emissions, trying to limit the global warming by 1.5 degrees Celsius, the frequency of extreme El Nino events actually keep increasing for as long as a century. And that is consistent with the result of Scott Power's study that the risk of ENSO-related major rainfall disruption appears locked in for at least the remainder of the 21st century. So that is a risk that we need to weigh. And lastly, IOD, as I mentioned, also have event diversity. And if we do not distinguish between strong and moderate IOD, we do not get a clear picture of what's going to happen with IOD in the future. So in this paper, titled in Nature Climate Change, we found that after you separate these two, the strong positive IODs increase, but the moderate BIOD actually decrease in response to greenhouse forcing. Maybe we can I can explain that in the Q&A if there's time for the mechanism, but maybe we can move on to the next slide. Okay, so what has NESS 5.2 done to us? It has actually facilitated us to improve our understanding of ENSO and IOD. And with that, we can inform future climate risk associated with potential changes in ENSO and IOD in a warming climate. But we also note that it's actually the impact occur on a background climate that is also changing. And that can exacerbate the impact of ENSO and IOD itself. For example, over Australia, the rainfall is projected to reduce in those regions highlighted in red. And also the air temperature is projected to increase. So that actually increases evaporation, which if you have a positive IOD occurring, then you will get even worse bushfires than in the present climate. Okay, so the point is that we need to identify sources of uncertainties toward more reliable projections. For example, as I mentioned previously, the Pacific is affected by things going on in other basins, and that can contribute to uncertainties. And also model biases. Our climate models are not perfect, right? So we need to understand them as well. Those are actually been documented in those publications. And it also allows us to facilitate cross-institutional collaboration on research as well as synthesis of current knowledge, identifying gaps and challenges, as I've already mentioned before. And also communicate our results to the broad public. We have actually quite a lot of media coverage. As an example, there is our book, if you can see, book I'm holding here. We brought in about 98 authors and writing 21 chapters on different aspects of ENSO in a changing climate. And that was covered by Peter Hannum in Sydney Morning Herald. And also, we engage with industry. For example, I was invited to give a talk at the Swiss Re Sydney office, talking about how will ENSO, IOD, and SEM change in a warming climate. I think this is the last slide for me, I think. Yeah, so I will pass on to Hayley on drought. Please, Hayley.
Thank you, Agus. So, okay, so drought. Look, this is, I suppose, a fairly recent addition to the NESS 5.2 project. Most of the projects explicitly examining drought really started in the last 18 months, kind of July 2019 or so. And I suppose one of the reasons that drought projects were explicitly included was because, you know, one of the key challenges that we had is that there is significant knowledge gap still around drought and around multi-year drought. And there really hasn't been a lot done in terms of looking at their representation in climate models and also future changes and projections in drought. A lot of it comes from changes in mean rainfall. So that's just the image that I've got on the right-hand side here, just from Gross et al. 2020. You can see the rainfall change between historical and high emission scenarios, where the redder, browner colours are drying and the greeny blues are getting wetter. And the stippling, the dots show where I think it's 90% of the models agree, and you can see some agreement in some regions more than others, I should say. This is for winter spring rainfall. But in that sense, a lot of studies have kind of only looked at changes in mean rainfall and inferred changes from drought. So we felt that there was a significant knowledge gap that kind of needs to be plugged, and we're starting to do that in 5.2 here over the last 18 months. So we also found that one of the significant challenges that we have is looking at future changes to the mechanisms that are linked to current droughts. So that's basically what Agus was talking about before, but you know, understanding those mechanisms is all well and good, but then linking those to, you know, periods of low rainfall and drought is kind of the next step. So the other aspect is also moving a little bit beyond the rainfall only examinations, including metrics that incorporate evaporative processes. And we also wanted to have a look at high impact droughts that have kind of only recently been acknowledged in the literature in the last probably 5 years, and really the last 2 years they've really kind of taken off, but newly acknowledged and high impact drought studies around this thing called flash drought, which I'll explain later on. So the approach we've taken is a really multi-timescale approach. So we looked at droughts on very short timescales, these so-called flash droughts, which are basically just rapidly onsetting droughts over the course of weeks, and agricultural droughts, so that's on the order of months. And we also looked at multi-decadal droughts, so this persistence in drought where we get kind of a millennium-style drought, 2 or more years. And as I said before, we wanted to take the approach of explicit investigation of drought rather than just mean rainfall change. So this involves some really key collaborations. Work at Monash University and at the Bureau of Meteorology was key for this, and collaboration between the two. But we also had fantastic collaboration among other institutes, which I'll talk about in a minute. But we also were able to have conversations which included industry and government. And these were really great and useful two-way conversations at a workshop that really allowed us to identify those, not all of them obviously, but some of the key unknowns that those end users were interested in. Next slide, please. Thanks. So I'm going to go through 3 main highlights, and the first is associated with these collaborations between cross-institutional collaborations. So this involved the Bureau of Meteorology, CSIRO and the universities. Basically, we identified at the start of 2019 that there was a lot of fantastic research on multi-year drought going on, but it was quite disconnected. So we decided to get everybody together and have a workshop. And we also invited several people from industry, including, for example, the Victorian Government Department of Environment, Land, Water and Planning, and a few others as well. And also people working directly with farmers and things like that. So from the University of Southern Queensland, working on the North Australia Drought Project, they all came along. And we had a fantastic workshop talking about, what the commonalities were, where the gaps were, and how we might move drought research forward in terms of multi-year drought. So we had people from paleoclimate perspective, we had people from climate modelling perspective, and we have people from observations perspective, and as I said, the end users as well. So the NESS 5.2 project really helped to facilitate that workshop that we had. I think it was 60 or 70 people in the end come along and present their work and have some really fantastic discussions there. So a few things that came out of the workshop, which we've subsequently written up into a review paper, which was an output for the NESS 5.2 that's currently under review in Weather and Climate Extremes. But one of the things we spoke about is kind of highlighted in these images on the bottom left here, these 2 maps. The left map basically shows persistence of months of very low rainfall, and the map on the right shows something a little bit differently, and it shows persistence of months without very wet conditions. So there's a bit of a difference there, and you can see the difference in scale. But what I suppose one of the things that came from this workshop was that there was this consensus that multi-year droughts are a little bit different to regular droughts in the sense that they're not always dry, but they are persistently not wet, if that makes sense. So in that sense, one of the key outcomes was that we felt that really looking at both sides of that drought coin, where we look at processes associated with the dry conditions, but also the lack of very wet conditions, because it's those very wet conditions that terminate the droughts. And so why we're not getting those, those particular systems through or whatever is something that we need to focus on. So we talked about broadening definitions of multi-year drought and defining characteristics. We talked about this concept of how bad can drought get, which was one of the questions that the end users really wanted to know. You know, is a millennium drought in southeastern Australia about as bad as it can get? And ultimately, the answer from both the paleoclimate and the modelling community was no, unfortunately not. In terms of kind of persistence of dry conditions, there seems to be evidence for the paleoclimate record and from modelling studies as well that we can get longer persistence of dry conditions. But the question of the magnitude of that dry, I suppose, under internal variability is a big question where we've kind of highlighted that knowledge gap. We also highlighted that there is a real need to explicitly examine multi-year droughts in climate models and to distinguish these from mean drying trends. A lot of the inferences about future drought and multi-year drought come from drying trends, and the answers don't seem to be always so straightforward. So yeah, those were a few things that came from this workshop, and we have put that in a review paper, as I said. Next slide, please. So we also highlighted the need in NESS 5.2 to explicitly evaluate very dry conditions, you know, very dry months and very dry seasons, very dry years, for example, in climate model studies. And just an example of that is from a paper by Delage and Power in 2020 in Climate Dynamics. So they explicitly looked at, for example, seasons, winter, spring seasons of below decile 1, so in the lowest 10%, and that's what you can see in the top right images there. So of the top right image, that 3-panel plot, you can see the far left is the historical simulations. In the middle is a high emissions pathway, the RCP 8.5, and the change is on the far right. And stippling, or those dots, indicate where you have 70% of model agreement. And in that sense, the agreement in the models of the driest seasons getting drier is quite strong. And so that was a really useful thing to look explicitly at those dry seasons. Also looking at the relationships between, you know, our common modes of variability, as I spoke about, El Niño, Southern Oscillation, and particularly El Niños and La Niñas. You know, what's going to happen to the relationship between low periods of low rainfall and high rainfall and those modes. And so this paper showed, just using 5 of the best CMIP5 models for ENSO, the criteria of which is in the paper, they showed both dry El Niños and La Niñas, but a bit of an asymmetrical change. So El Niños got drier, and La Niñas tended to get a little bit drier, but not as dry as the El Niños. So next slide. And so the final challenge that we looked at was this idea of these more agricultural droughts or flash droughts, and really starting to tie in those types of droughts, ideas of temperature and evaporation playing a role, because they do seem to play a much stronger role in these rapid onset droughts. So we look specifically at these flash droughts, which are just, you know, droughts that seem to go from kind of regular soil moisture conditions to very dry soil moisture conditions over a matter of weeks. And some work in NESS 5.2 has really been looking at developing a climatology of flash drought for Australia, which is currently under review in environmental research letters currently at the moment. And we looked at a comparison of drought metrics, basically evaporation-based metrics that have been used in the United States to look at flash drought in Australia, and found some interesting things, you know. And then we looked at a case study of the Wimmera region and looked at these flash droughts that can occur seemingly during wet conditions. And in the bottom left plot, this is just the proportion of area under flash drought in particular years, and I've just highlighted one year, 1993 there, and that's a really interesting flash drought because that came off the back of quite a wet year in 1992, and from March to May the region descended into drought very, very rapidly. So identifying that those kind of conditions exist and can happen is a really important part of NESS 5.2. And it also presents new questions about the relationships between these kind of rapid onset droughts and heat waves and warm temperatures as well. Just on the bottom right, I've got a plot here that shows just correlations or the relationships between various metrics that measure flash drought. Don't need to worry about what they are. But if you just look at those two red dots that are circled, basically what it shows is that metrics that are based in what we call evaporative demand, so basically how thirsty the atmosphere is, they seem to have a strong relationship in the southeast, so this is for the Wimmera region, with La Niña, funnily enough, rather than El Niño. And we think that that might have something to do with the fact that La Niñas in the southeast of Australia are often accompanied with short, sharp heat waves that are related to tropical cyclones in northwestern Australia, which has been shown for a while. But that's something we'd like to continue to look at because, you know, this relationship between heat waves and drought. But next slide, please. So just to go on the impact of the drought program, we really saw some good science impact in terms of strong interdisciplinary collaborations across institutes and across various research groups, including paleoclimate modelling and observations, that's resulted in this review paper. And it was great to see NESS 5.2 facilitate explicit examinations of kind of multi-year drought and future drought in climate models beyond kind of this examination of mean rainfall. And NESS 5.2 really allowed this identification of metrics and identification of this new, well, it's not new, this newly acknowledged, I should say, type of drought called flash drought that seems to be very high impact. And in terms of end user impact, it was really great to see those stakeholders involved in those discussions, particularly around the multi-year drought. And with the flash drought stuff as well, being able to disseminate those findings to partners who then directly collaborated with end users like farmers via, for example, the North Australian Climate Project. I've gone a bit over, sorry about that, but I'll hand over to Pandora now. Thanks very much.
Thanks, Ailey.
Thanks, Ailey. I seem to have just lost my camera, unfortunately, so I'm going to try and change cameras and switch myself around. Give me a moment.
All good.
Okay.
Thanks, Pandora.
Okay, I'm just going to move the screen so I can not be staring at the side of my face. There we go. So, thanks, Agus and Ailey. I think this is really great background into considering the question of what is causing a particular extreme. And Ailey's described a lot of the background thinking for drought, but what about other features like heat extremes, rainfall extremes, even ones that are very complex like fire? And we can think about the methods that we might use to do that and what each of those methods can bring us. Starting very simply, we can look at the CMIP archive and have a look at the thresholds for any particular extreme event that's identified as an aerial average over a region, crossing that threshold like we did in spring of last year. And David Crowley wrote a great piece on that, presented on the NESS website, comparing how the distribution of heat extremes of that nature look in the historical period, but also if we considered a world where there was no greenhouse gas warming or other anthropogenic change. And we can see in the bottom right the distribution shift in our probability density function, where the likelihood is far higher in the current climate than it was in a world without greenhouse gas increases in the green there. Next slide, please. So that method is reasonably established and it's very, very useful. It's very quick to get an answer how the likelihood has been changing due to anthropogenic forcing. But what are some other things that we can do with approaches like that? One novel thing we've done is to look at not just a single event as a month-long heat wave, say, but look at a 20-year shift in the actual rainfall. So, as Ailey suggested, simulating rainfall can be quite tricky. If we look at a longer term average, some of those concerns are ameliorated, and this is a 20-year average. If you can see, I don't know if you can see my mouse, but in the left-hand panel, we have the 20-year average and the rainfall distribution you get in that from the recent period. So this is in Southeast Australia, the Millennium Drought is in there, and you have some very, very low rainfall totals. Whereas compared to every other observed 20-year period, it's much, much drier. We can then look at the CMIP models with different forcing. And so those that have greenhouse gas forcing or full forcing, and you can look at the historical period in the bottom panel here, and this is what we would normally expect, but that most recent 20-year period is on the far left there as the driest period on record, and how often was that represented with various greenhouse gas factors, and we found that there was a signature in that rainfall decline. As I said, simulating, next slide please. Simulating rainfall is quite hard, so across the project in 5.2 and building on work from 2.2, we actually developed a new technique to investigate the event in detail. And so previously you could look for a kind of class of events, but this system actually forecasts the event that we're considering. It forecasts the event using a subseasonal ensemble forecast, and in this case we've used two different models, so POAMA, which is a low resolution model, and ACCESS, which is the operational forecast model of the seasons for the Bureau of Meteorology. And we modify the background mean state by taking off an estimate of the climate change we've seen over the last 60 years or so. In the right-hand panels there, you can see the sea surface temperature anomaly is generally much warmer, except for places in the Southern Ocean, and the salinity has been changed as well. We see freshening in the Western Pacific there. I would like to add that this is a fully coupled system, so it's a full 3D change that we're making through the ocean. We also change the atmospheric temperature. On the left-hand side, we can see the air temperature anomaly, so warming throughout the troposphere and then cooling aloft, as you would expect with climate change, and an increase in humidity, particularly through the tropics. With the POAMA system, we could also modify the land surface. And I've thought a lot about what this means, like how does the land change on a long-term basis? I tend to think that it changes. This is soil moisture in the very top right there. You can see a drier state is what we're going forward with. And I tend to think that that's actually due to long-term conditions. And I like to think of it as if you were in a cave. So in a cave, you have the temperature, air temperature is the average from the full year. And this is what we're seeing in the soils. So you're actually starting each event on a background of a slightly drier, generally environment. And so in those deep soils and deeper layers, it will also be warmer. Next slide, please. So what can you do with these sorts of systems? So we had a look at the very dry spring in Tasmania. So we're looking to examine the causes for a lack of rainfall, and that's quite tricky. On the right-hand side, we've compared the amount of rainfall on the vertical axis with the mean sea level pressure on the horizontal axis, and the red dot is 2015, which was the driest October in Tasmania, and obviously it's linked to very high pressures. And so using our system, which you can see on the right is the mean sea level pressure anomaly, which was produced by the forecast of the current climate minus the forecast of a climate where there was not the increase in CO2 we've seen through industrial times. And what you can see there is a pattern that is very reminiscent of the southern annular mode positive phase. On the left is a different system. This is called weather at home, and it is a very different setup to what we've set up with the forecasts, and it's actually got set boundary conditions with the sea surface temperatures with an anomaly produced based on changes you see in the CMIP models. And so with these two systems, we can actually explore a whole lot of different variables. So we looked at the mean sea level pressure over Tasmania, the Pacific South America pattern, the subtropical ridge, the southern annular mode, atmospheric blocking, and the Indian Ocean dipole. And what came out was it was really this shift to the high mode of SAM that was very important for the drying in Tasmania and is linked to climate change, and also changes in the Indian Ocean dipole. And we're learning more and more about how those changes are influenced by climate change, as detailed by Agus. Next slide, please. So that got us thinking about the trend and then what that means for an event and how the circulation changes can impact that. But I can't go into that slide because we don't have very much time now. So I might just jump over that one and go to the next slide. And just talk about the impacts that this attribution work has had. I guess we've had the chance to develop some novel techniques, and this really aids the understanding, particularly for these wet or dry or complex events, including fire. And so we can start to talk more about the nuances of how the climate change influences these extremes, and that circulation changes are important. One really big factor has been a lot of international engagement. So a lot of international collaborators are very excited about our methods, and we're involved in the International Detection and Attribution Group and the IPCC attribution team working on the current assessment. We've provided advice on attribution studies of Australia's fires to our international colleagues, and we've advised governments on the latest attribution assessments that have been coming out. Next slide, please. So looking ahead, so this is a summary across the whole of the Project 5.2. From the climate variability research, we would like to better understand the ENSO and IOD processes. There's still so much to learn. How they're represented in models, and re-evaluate what the CMIP6 models are saying. We'd like to improve understanding of how ENSO, IOD and other drivers interact and how this might change in future. We'd like to see how those changes manifest in extreme events like droughts and floods. We'd better like to understand the uncertainties in future projections, including the role of internal variability. For drought, we'd like to see the effects of rising temperature and heat waves on summer droughts where evaporative demand is important, which we've found in the recent research, and examine the impacts of flash drought. And so what are those challenges for stakeholders, particularly in the agricultural sector? Explore the relationships between multi-year drought and aridifying environments. For attribution science, the rapid turnaround assessments, which is what so many groups would like, what will trigger such an assessment? We would like to update our pre-computed estimates, as I showed you that David Caroli drew on, to use CMIP6. We'd like to develop our experimental forecast system further and have that as a tool that we can use very quickly. And we'd like to answer some of the fundamental science questions. How can we explore those trends versus events, or how IOD and ENSO interact with these extremes? And then at the very nitty-gritty level, think about the assimilation methods and the model and method evaluation. Thank you.